Hi everybody! In this video we're going to talk about what happens when we put a dielectric inside a capacitor. So first let's talk about what a dielectric is. It's simply just an insulator that allows for its molecules to be polarized. So it's an insulator, meaning that it's not going to allow the flow of charge from one side of the plate to the other, but it can have its molecules polarize. And to remember what polarize means, we're going to just say, let's for example say that there's an electric field like so. Then if the molecules polarize, normally we might just have the plus and the minus sort of randomly around in different orientations. And then when it becomes polarized, then the positives they're sort of like attached, but they're on leashes with each other. So they go the way they want to go, but they still stay attached. So the positives will go with the field and the minuses will go against the field. And so all of the molecules or atoms just sort of line up in that fashion. So that's what a dielectric is. And now let's look to see what happens when we put it between the plates of a parallel plate capacitor. And this will work for what we're going to show for putting it between the plates of a parallel plate capacitor, but it'll work for any capacitance configuration, whether it's a spherical capacitor or a cylindrical capacitor, etc. So what I'm going to do is draw our capacitor. And I'm going to draw it fairly large because a lot is going to show up in this diagram. And I'm just going to pick a plate to have us call the positive plate. So I'll go ahead over here and call this my positive plate. And over here, I'm going to then call this one my negative plate. And that just depends on how I initially charged it up, right? I applied some voltage across it. And so that allowed me, remember that's like the hill analogy, that allowed me to have one plate that collect positive charge, one plate that collected a negative charge. And so I'm going to then have an electric field that's created between these plates. And so I'm going to draw this electric field that's created between the plates. And it goes from positive to negative. So this is my electric field. That is going to be my electric field from the plates, right? And now what I'm going to do is insert, and I'll kind of just show it in the bottom half. I'm then going to insert a dielectric material down here. So let me say that this is a dielectric material, and I'm just going to leave the top alone so that we can see what it looks like without that and with the dielectric. So this is going to be my dielectric material, which is again just an insulator that I'm sticking between the plates. It could be something as simple as paper, as we'll do in some of our activities. So that's my dielectric material. And so according to this idea of polarization, what's going to happen inside of these plates, and now my electric field's going to the left, all the positives are going to line up to the left, and the negatives are going to kind of line up to the right. And so what we end up with is this sort of polarization taking place. And the net impact of all of these little polarizing molecules or atoms is that essentially I get as if there was, a slight positive side to one of the sides of the insulator and a negative side to the other. Now, very importantly, look at which way these guys polarized, right? They polarized so that their positive side is actually near the negative plate. So I'm going to zoom in on this and make that note. So note that the positive side of the polarization is next to the negative plate. So what happens now is we end up with an electric field being created by these polarized molecules. So important idea here then is that we have an electric field is going to be created by these polarized molecules. And so I'm going to now sketch that electric field. It's not going to be as big as the electric field it's in, but it is still going to have an impact. And so this here is going to say be my electric field from these polarized molecules. So that's those lines pointing opposite. And so as we build this up, if I kind of take away the picture of the dielectric in the space and I just simply look up here, right, that I would then have some smaller electric field from the polarized molecules. So that's my electric field from the dielectric because it is the one that has the polarized molecules. Then what I end up with is I end up with a net result of having a lower electric field. So a lower net electric field. That's a big deal because if I have a lower electric field, then essentially my plates, if they're stuck at the same voltage, then what that means is they're able to pull on more charge until they get back to the electric field they're supposed to be at. Or if you apply that voltage to start and then disconnect it from the battery and then put this dielectric in, then what's going to happen is that net electric field being lower essentially lowers the voltage on the plates. So let me go ahead and show what I mean by that. So let's say that this was disconnected from a battery. I had initially applied some, V minus, and I'll call that initial, V minus initial. And then let's call this some V plus initial that I had initially applied. And so originally, before the dielectric, the electric field from the plates, remember between the plates, we can have this result that the voltage, the delta V between the plates, initially would just be equal to this electric field, and I'll call that E sub P, E sub from the plates, times the D, the separation between the plates. There's just that kind of linear, nice relationship when we have that uniform electric field between voltage and our electric field. So the delta V initially was equal to sum of the electric field between the plates times D. Then I applied my dielectric, which is going to lower the net electric field. And so that means that my delta V final is going to be equal to some lower, I'm going to call this E net. The D has not changed. So my E net is now lower, which means that delta V final is now lower also. So my actual voltage across these capacitor is lower when I insert that dielectric. Assuming that I charge it up, I apply my voltage, I take my capacitor away from the voltage, so it's just sitting there with the two charged plates. I put the dielectric in, and all of a sudden, my voltage is going to be lower because of this polarizing effect. So what does that mean in terms of capacitance? Let me go ahead and make some space to discuss that. Remember then that capacitance is simply a relationship between how much charge an object can hold given some potential difference across it. So in this case, the plates are holding the same Q, but now at a lower delta V. So effectively, I've raised the capacitance of this device. Just by inserting the dielectric. And something that polarizes more, so the key thing here, right, is that it raises the capacitance, and the more polarization, the more something can polarize, then the more increase in the capacitance, because the net electric field gets lower and lower the more that something can polarize. And so what we define then is this dielectric constant, which is just going to go with, it's a kappa, so it's like a small little capital K in Greek letters, so it's a kappa. And the kappa for vacuum is going to equal 1, and the kappa for air is just about 1 to any digits that we're going to keep. It's, at least 1.00. And so both of those are, not, the vacuum has nothing that could even polarize. Air polarizes very, very little. And then a typical kappa, right, would be something greater than 1. And so we would have then say kappa greater than 1 for other things. And so that kappa is actually just going to now adjust our equation for capacitance. So we're going to say here that for our capacitance, we would have our capacitance in a dielectric is equal to kappa times C naught, and that would be our capacitance in vacuum. And so for a parallel plate, that simply means that C is going to be equal to kappa epsilon naught A over D. So instead of just epsilon naught A over D, we now have kappa epsilon naught A over D. Okay, I hope this helps.